In this final section of this chapter, we're going to look at polyprotic acids, which are acids with more than one proton, in this case H2SO4. Before we do that, I want to talk a little bit more about where we're going with all of this moving forward. In the next section, we're going to look at some more advanced aspects of equilibrium. And we're going to look at what happens if you mix acids and bases together in things like titration reactions. And you may have done something like this in the lab where you mixed a strong acid and a strong base together. But we're also going to look at them in terms of what happens if you mix a strong acid with a weak base or a weak acid with a strong base, and look at different titration curves that occur for the different types of mixtures. Also, we're going to look at buffers. What happens when you start mixing weak acids and conjugate bases together? And then finally, we'll look at one other additional aspect of equilibrium, which involves dissolving compounds and the solubility product constant. So those are the general ideas for the next chapter. So equilibrium isn't going away, and there's no great distinction between this chapter and titrations and buffers and things like this, but I think it's good to have them separated out just so you're not overwhelmed with material on an exam, for example. So let's take a look here at polyprotic acids. So the first polyprotic acid we're looking at here is sulfuric acid. So the first proton of sulfuric acid interacts with water to form H3O plus and HSO4 minus. HSO4 minus still has a proton to give. So HSO4 minus itself can interact with water to form H3O plus and SO4 2 minus. Note that H2SO4 is one of our strong acids, and the Ka, is more than 100. So this is complete dissociation. The second Ka here is 1.2 times 10 to the minus 2. This is actually a fairly strong weak acid, which again, I know doesn't make a lot of sense, but it is a fairly strong weak acid. But if we look at Ka1 and Ka2, Ka1 is more than Ka2. Well, this makes perfect sense. Once this already loses a proton, it's going to be less likely to lose another one. It's already got a minus charge, and when it loses a proton, it loses H+. Something that already has a minus charge is going to be more likely to hold on to that proton than something that's neutral. So Ka1 is greater than Ka2, and that's always going to happen. If we think about it in terms of pKa, though, it's going to be the opposite. pKa1 is always going to be less than pKa2. Okay, the pKa of 100 is, if it's exactly 100, is -2. So this is going to be a smaller number than this one, which is going to be somewhere around +2. Not exactly +2, but around +2. Let's look at a weak acid, carbonic acid. Carbonic acid forms when we dissolve carbon dioxide in water, and was actually at the beginning, in the beginning slide of this chapter. Carbonic acid is a diprotic acid. So its first proton, can come off to form H3O plus and H3O3 minus. And this is more of a traditional Ka expression. It's not really a lot of sense in writing a Ka for a strong acid. We can just think of whatever the concentration of the acid is the concentration of, can be used to calculate the pH, which is true. But in this case, we do have a weak acid, and here's the Ka expression, and the value is 4.3 times 10 to the minus 7. The second ionization here is for HCO3 minus to give another proton to water to form H3O plus and CO3 2 minus, which, just like before, is a smaller value than the first ionization for the same reason. This is already minus, and it's going to be less likely to lose a positive charge than something that's neutral. That being said, if we look at the orders of magnitude here, all right, this is 4 orders of magnitude, or 10,000 times less than this one. So what does that mean? Well, it means that the pH is going to be for the first proton. Okay, the one that's going to change the concentration of H3O plus by far the most is the first one, because the pKa here is 10,000 times smaller. So therefore, we could calculate the pH of a solution using the first ionization of this weak acid. Now, this may not be true 100% of the time, but it's a good general rule that this is going to be that this is going to be true unless you happen to have a case where the pKa's are much closer together than these two are. But when they're 4 orders of magnitude off, it's certainly going to be the case. Let's look at a triprotic acid, phosphoric acid. In this case, you can see H3PO4 has a Ka of 7.5 times 10 to the minus 3. H2PO4 minus has a Ka of 6.3 times 10 to the minus 8. And HPO4 2 minus has a Ka of 3.6 times 10 to the minus 13. So again, the one that's primarily going to change the pH is the first one because it's roughly 5 orders of magnitude more stronger of an acid than you would do for H2PO4 minus. And again, this is just a general trend. So there isn't a huge amount about polyprotic acids. We're not going to do any calculations here with polyprotic acids, but it is worth noting that there are polyprotic acids. And for the examples presented here, each of them, the most of the change in the pH is going to be from the acid, the original acid, when the first proton comes off. The second and the third protons are going to have negligible effects on the pH because their pKa's, or their Ka's, excuse me, are so much smaller. Okay, or their pKa's are so much larger if we were looking at a chart of pKa's. So that concludes this chapter with this kind of qualitative section, but I think there are plenty of calculations in the previous sections. These calculations take practice, so please be sure to practice with these types of Ka, Kb, pH, OH minus, concentration H3O plus, all these types of calculations.